Discovery's 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Hello and welcome everyone. And thanks for joining me for my talk on fuzzing automotive software. So in this talk, we will be focusing on one main question, which is given the complex and special nature of automotive software, how can we come up with a setup that enables us to fuzz the software in an effective and efficient manner? And so, of course, we'll discuss the challenges that are associated with fuzzing automotive software and discuss an approach that we developed in order to tackle these challenges. And we will demonstrate this approach with a practical examples and a live coding session. So first, just a few words about myself. So I am one of the co-founders and the chief scientist at Code Intelligence. Prior to Code Intelligence, my work and research was mainly focused on binary code analysis with the focus on malware analysis and vulnerability discovery. And at Code Intelligence, I mainly work with our great team on developing our fuzzing technologies and so that we can make them more effective and usable and enable them to support more industry use cases. And of course, you can, for discussions and exchange, you can reach out to me via email, Twitter, and LinkedIn. So if we have a look at the current situation or the current landscape of automotive software, it's become clear that we see a significant increase in threats and IT security threats that target this software. And so nowadays cars are becoming more and more connected and they run more and more complex software. While this, on the one hand, really good so that we can develop new features and support, for example, autonomous driving. On the other hand, it results in a much bigger attack surface that attackers can use to exploit security vulnerabilities and hack into the car. And this is not a theoretical threat anymore, as we see in these examples. So, for example, a few hackers were able to remotely kill the engine on a Jeep on the motorway, or security researchers were able to hack into a Tesla car using an exploit that was delivered with a drone. And luckily, these attacks have been performed by security researchers, but they show the possibility that such security vulnerabilities or bugs can be exploited by attackers. And so when a security vulnerability stay undercover and reach software that actually runs in a car in production, it's already too late. and it becomes more difficult and expensive to fix and patch these vulnerabilities. And of course, in addition to the damage that it might cause to the reputation and image of the manufacturer. So as an automotive developer, we would like ideally to shift or to find as many bugs and security vulnerability as we can as early as possible in the development process so that they can be fixed quickly and never reach production. And of course, for that, we would need automated tests, and this would be, as I mentioned, the focus of this talk. So before going into the technical details of why it's challenging to test or to fuzz automotive software, let's have a look at the broader picture first. So and discuss why currently automotive security or software security is hard, slow, and expensive. We see a growing number of industry standards that puts regulations or standards that automotive software need to satisfy for it in order for it to be actually allowed to be deployed in the car. While this, of course, is good that we can increase the quality of the software there. This process is quite complicated, time extensive, and as a result, we'll have slower release cycles. So features will get delayed until they deployed in the car. And of course, from the developer point of view, so the car manufacturer also they have increasing requirements regarding the quality of the software that needs to be run in the car. And we're dealing with a sort of a new IT security landscape here. So not all of the security threats are known, and we need sort of an automated approach to find them. In addition, automotive software is, as I mentioned, is becoming increasingly complex, and it's ineffective to just limit the process of security testing to manual effort or pen testing. So, having a look at these challenges, fuzzing provides a really scalable and effective approach for testing. And so, as we've seen both in academia and industry, fuzzing is currently the best method or the most effective methods to find bugs. So from the academic point of view, we see an exponential growth of research that are published at top conferences that target, that work on fuzzing, and also in the industry. So tech leaders like Google and Microsoft, they find most of their bugs with fuzzing. So, and even some projects at Google, they find around 80% of the bugs with fuzzing. And it's clear from the examples we show here that fuzzing is able to tackle complex software like the Linux kernel, the Chrome browser, Microsoft Office, or the Mozilla Firefox browser. And here on the left, we see some examples of high-profile security vulnerabilities that stayed for few years in the software, but can be found by fuzzing very quickly. So a Heartbleed was a dangerous security vulnerability in OpenSSL that stayed uncaught for 3 years, but with fuzzing, it was demonstrated that you can find these bugs in actually 10 seconds. And a more recent example that we did was the Log4j security vulnerability. And so with our open source Fuzzer, Jazzer, now you can find this vulnerability in less than 5 minutes. So, and here I also encourage everybody to have a look at Jazzer. It's open source on GitHub. So we see here it's clearly that fuzzing is really effective in in finding bugs and security vulnerabilities. So what you'd like to actually achieve in order for it to be effective, it's necessary that it's applied continuously as part of the development process, so that code that are checked into a repository before it lands in the main branch, it can be tested, it can be fuzzed, and so developers would get feedback quite early in the development process, and this will enable them to fix these bugs much more faster. And the idea here is that we can use automation, or in this case, continuous fuzz testing, to find the majority of bugs, most of 80% of the bugs, and save the pen testing efforts and save the resources for the pen testing effort to focus on the remaining 20% that actually requires human intelligence. And yeah, human intelligence is the most valuable but least scalable resource. And by freeing human analysts from dealing with all the bugs that fuzz testing or automation can find, they can focus on actually targeting the rest that cannot be found by automation. So so we had I hope a good overview about why fuzz testing is effective and that it's effective. And so before we dig deeper into fuzzing automotive software, I'd like to just give a brief introduction into fuzzing. So what is fuzzing, and how can you write simple fuzz tests? I'll show that with two practical examples. So the main idea of fuzzing is really simple. So that you have a software under test that you'd like to test, to fuzz, and you have a fuzzer. And the fuzzer just throws some random input, some random data onto the system under test, and with the aim or with the hope that some of these inputs would lead to a crash. And when this happens, then we have found a bug, and we have found a concrete input that triggers this bug. And so this is how fuzzing actually starts more than 30 years ago, and was able to find many bugs in Unix utilities. But if we have a closer look about this approach, it has two fundamental limitations. So the first one is the fuzzer does not have any idea about how the system actually behaves with respect when it is executed with a given input. So it does not know if a new input reach good code coverage or not, and if the system under test expects some structured data, for example, as an image file, then it's highly unlikely that the fuzzer by a chance provides a valid image. So most inputs in this setup will be rejected quite early in the testing process, and you will be able to only find some shallow bugs. The second limitation here is that not all security vulnerabilities or not all bugs lead to a crash. And these are actually the nasty bugs, or the dangerous bugs that we'd like to protect against. So if we take as an example, for example, a heap buffer overflow, that's where you can write to a heap area or read from a heap area that you're not allowed to. These bugs do not necessarily result in a system crash, but these bugs can be exploited by the attacker in order to hack the system or to execute remote code. So with these two limitations in mind, so the next step into improving the fuzzing process, to make it able to reach more code, two changes were made. So let's take the example of black box fuzzing. where we test in image parsers, we can either design a special fuzzer that knows the structure of the image, but then we have to have a special image, special parser or a special grammar for each application or for each type of application that we fuzz, or we give the fuzzer a head start by providing some test data. So for example, in the case of the image parser, as a developer, I may have some unit tests that has some images. I can use these images as an input or as seeds for the fuzzer, and the fuzzer can then do some mutations, flip some bits and bytes, change the color, for example, with the hope of triggering the crash and having good code coverage. But this is a little bit better than what have you seen before, but it still has the same fundamental limitations: limited code coverage and missed bugs. And so the real breakthrough with fuzzing was with the idea of using instrumentation to give feedback to the fuzzer about what's happening inside the application, or how the code is reacting to a given input. So what this means is that when we build our program, we instrument the code, and this means that we inject in the code special markers that give the fuzzer information about which areas has been covered by a specific input, and also more information about specific compares that's happening in the code. So the fuzzer, with this information, with this feedback, it can sort of evaluate the quality of each input it generates, and iteratively it improves the input so that the code coverage is maximized. So in this example, let's take the image parser as an example. So a fuzzer would then start, let's say, with the null, and the application is executed, and from the instrumentation, it gets the following information. So it gets, with this input, you are able to cover these lines of code, for example. And that few here, the code is compared to against some magic numbers, I guess some static numbers. So this is the fuzzer then uses this feedback, to say, the input is compared against this constant magic values. So what would happen if I use this in my input? So in the next iteration, the fuzzer can then generate this input, provide it to the application, and now it gets feedback that now new code, now we see the return here, new code has been executed. So at this stage, the fuzzer sort of convinced the application to treat the input as an JPEG image. And with this loop, the fuzzer then at some point it can generate a valid image, and it uses all this feedback in order to explore the state of the program and to increase code coverage. And our fuzzers are really fast. They can execute hundreds of thousands of times per second. And with this feedback loop, they sort of learn about what inputs or how the inputs should be structured that are accepted by the application. And this actually reflects a real experiment that was done with the open source fuzzer EFL, where it was used to test a JPEG parser, and after a few hours using this feedback loop, the fuzzer was actually able to generate valid images. So this gives you a sort of an intuition about how effective how effective fuzz testing actually is, or coverage guided fuzzing actually is. And here in the instrumentation, we can also inject more runtime bug detectors that gives us more information about certain errors that can happen, for example, heap overflow and stuff like that, as you will see in shortly. So from a developer point of view, you can think of an analogy between testing and fuzzing, or between unit testing and fuzzing. So when we write unit tests, we basically execute or call our API that you'd like to test with a specific set of inputs, and then we check some conditions that needs to be satisfied. And with this, we can, test different variants of what can happen with the API. With fuzzing, you can think of it as an endless loop. So the fuzzer continuously calls the application or calls the API that I want to fuzz. And each time a new input is generated based on the feedback that the fuzzer has learned in previous iterations of the program. And this code is generated, so that code coverage is maximized. This just to give a sort of a mental comparison between fuzz testing and unit testing. Okay, so let's get a little bit to the practical part. So we'll see a few examples here in this shortly, and for these examples we'll be using libfuzzer. So libfuzzer is a coverage guided fuzzer that is part of the CLang and LLVM project, and it's developed by Kostya, who is currently at Google. And it performs compile time instrumentation, meaning that the instrumentation happens when I compile my code. So these markers are injected during compile time, and it's in process, meaning that the fuzzer runtime and the application under test run in the same process, as we'll see. So you get a binary that you can execute, and this binary includes the test, or the code under test, and the fuzzer runtime. And you can use it, you can with that write fuzz tests to test specific functions. And the main idea here is that these fuzz tests that we will see in the next slide is checked in with the code, so that you can think of it as a normal test that you check in with the code, and these fuzzers or these fuzz tests fuzz the current version of the code that you're checking in, and this makes it very suitable, really suitable for continuous fuzzing or for CI/CD integration, where you check in your fuzz test. This fuzz test will be then compiled and run as part of a CI pipeline. And one thing that's really important here that make fuzzing also very suitable for CI/CD integration is that the fuzzer, all interesting inputs that the fuzzer finds, they are kept in a corpus. It's a directory that contains where the fuzzer writes file for each interesting input. So for each input that triggers a new behavior in the program. And so mean that at later runs, the fuzzer does not start from zero to learn about the program, but it starts with that corpus, meaning that it starts from the accumulated knowledge that the fuzzer has gathered over time. So you can do regression tests really, really quickly. So what do we need to do in order to write a fuzz test using libfuzzer? So what we need to do is we need to write a function that has this signature. It's called LLVM fuzzer test1 input. And it takes two arguments. It takes a data buffer and a size. And here inside this function, I can call my API, my function that I would like to test. And you can think of this function as an entry point for the fuzzer. So libfuzzer will then call this function in an endless loop. Each time it will provide new data, a new buffer, and it gives you also the size of this buffer that you can use to call your API. And of course, it generates this data and size based on the feedback in order to maximize code coverage. And that's all what you need to do. And what's remaining is that you can compile the code with CLang, and there is this this flag -f sanitize fuzzer. This actually includes the fuzzer runtime, so that the fuzzer injects its runtime here or links its runtime here, which is the main function that actually calls this function in an endless loop and does all the coverage optimization. We've mentioned previously that in order to detect hard to find bugs, we need sort of bug detectors. And in the context of C+ and the fuzzing community, these are known as sanitizers. And one of the sanitizer that you can use to find this memory corruption error is the address sanitizer, and you just activate it by adding a flag to the -f sanitize flag. And so now that we've seen how this looks in sort of on paper, let's see it in action. So here we have an example. So it's a simple C++ file here where we write a fuzzer. We write this LLVM fuzzer, this one input function, and we call this fuzzme function. And the fuzzme function simply checks if the data buffers actually start with a bug. And so this represents an example that occurs quite often, where which is like an off by one error, because this checks will be valid, will be okay for all for all values of data size, except when it's exactly 3. Because in this case, when it's exactly 3, then we are checking for characters, meaning we're reading 1 byte more than we're allowed to. And these off by one error are we see quite common in the software we test. So now, if you want to take this example, let's go to me. So here we have the source file, and now I say, okay, I would like to compile this first without the address sanitizer, just with the fuzzer instrumentation. So what this produces, it produces actually a binary, and inside this binary we have both the code that I would like to test, and the fuzzer runtime. And all I have to do now is just start this binary, and the fuzzing process starts. So now we see that the fuzzer is executing the binary, and we get information about the progress. So here we see that the coverage or the edge coverage is increasing, and we also see here the executions per second. So the fuzzer is managing over 2 million executions per second for this simple target. But it's not able to trigger the bug because it's not equipped with the bug detector. So here in this case, it will detect hard crashes, but such read overflows will not be detected. So in order to fix that, let's go back here. We can now say, okay, I would like to add to the fuzzing runtime the bug detectors or the address sanitizer. Now, if I run this application, we see that the fuzzer is very, very fast in finding a crash. And what's nice here is that we get the value, the concrete value that actually triggered this crash. And if we look here, now we have a file that contains the crashing inputs. Even better, we have here the complete stack trace, so the exact sequence of codes that happened in order to trigger this code. And we see that the bug has happened at line 9, which is exactly the line where we were performing this read. And it even tells us it's a heap of overflow, and you're reading one byte more than you are actually allowed to. And so with this information, a stack trace, a concrete crashing input, what I can do as a developer, I can start a debugging session with this example in order to understand what's happening in my code and this gives me with this concrete example, it's become easier for me as a developer to understand what's actually happening here inside the code. Okay, so if we go back here to our example, we see that we're calling the function under test with the data and size. So it's a data buffer and the corresponding size. But of course, this is not always the case, or usually I have APIs that expects more structured data like structs or integers or long, etc., or strings. And in order to handle these cases, we have the so-called Fuzz data provider. And it's also part of the CLang, and it's a single header C++ library that you can use in order to get values or fuzzing input of different types. So the idea, so this library contains a class that you can initialize with a data buffer, and you can initialize it with the fuzzer generated input. And once you do that, you can actually call the methods or use the methods that are provided by this class to get structured data. So you can get a consume boolean, consume integer, pick a value from some choices, and this enables you to really develop very effective fuzz targets, even if your API expects more structured data. And so let's see how this actually looks like. So here I have another example, which take, so here the fuzzme function now takes two parameters. It takes a string parameter called workshop and a size t parameter called year, and it compares if this string is compared to ASRG and the year is 2022, then we call this this line in order just to cause a crash. And so what can we do here in this case? So all I have to do, as I mentioned, we can include this fuzz data provider header. We can initialize this with the fuzzer generated input, and then we have these useful functions. We can now say, okay, I would like to consume a value or an integer in this range between 2000 and 2023. And the remaining bytes, I would like just to consume them as string. And now I have two variables of type size t and string that I can use to call my API. But of course, you can take this into arbitrarily complicated use cases and use the helper functions to construct your input, your structure input. So, and here's the same thing. So if we go to the second example, and now I have the header file and I have the source file. Also just need to compile it with CLang, and I get a fuzzer. Which means that it's an executable that I can write, that can start, and very quickly we get the expected the input that actually crashes the application. And you see that here it's a segmentation fault, and that I am trying to write to this unknown address, which is 2. And we see also the exact location, so it's at line 7 here, that actually triggered this bug. Okay, so now that we have a sort of an introduction to fuzzing, to libfuzzer, so what can we do with libfuzzer? Let's take a deeper look or a more a deeper look into the challenges that we have when fuzzing automotive software and how can we address those. So we have in automotive software mainly 3 challenges. So, and this is also based on our experience with the automotive projects that we have. First, you have hardware dependencies, meaning that we have some low-level code or some code that can only be executed on a special hardware. And for example, some code that gets the sensor data, for example, from a specific sensor. So this needs to run actually on the actual hardware. And what we've seen in our example is that we needed the software, we compiled the software under our test machines, so under Linux and x64. And because on these systems, on our test machines, we can get really effective and efficient fuzzing. We can get, as we mentioned, up to few thousands or hundreds of thousands of executions per second. And we will lose this efficiency if we run it on the actual hardware. So this is a big challenge because this part of code cannot be actually compiled on our test machines. And so we've seen in this example, we wrote a fuzz test that fuzz a specific function. And we mentioned that the automotive software is becoming increasingly complex. So if I want to write for each API, for each function, for each public function in my module, write a fuzz test, this can become really very time consuming and a manual effort. And it's one of the blockers that we've seen for automotive software to actually adapt fuzzing. So this is impractical, and it becomes even more difficult with statefulness, because what we've seen in the example is that we have a fuzz test that calls a single function. Normally in bigger software where we have a state, these functions should be called, they are called in a different order. And so I may need to have this in mind in order to be able to write some initialization code that brings my application into this state where it can be fuzzed, or I need to think about all the possible scenarios that can happen there and write fuzz tests that sort of mimics these scenarios. And these three challenges are the main challenges that we've seen so far in our automotive projects. So what have we done to address these challenges? So our approach here, and it's I emphasize here, it's one approach that we found really effective and really easy to use, and we can get results very quickly. And the approach is for addressing the first challenge where we have the hardware dependencies, and in order for us to be able to run these on our test machines or on the test server, we need to create mocks for this hardware and these library dependencies. And these mocks, ideally, they are not static. So one can think of a mock that, for example, if a function returns an integer, it just returns 0. But we need to run or to simulate all possible circumstances that the software is running under. And for that, in our approach, in our mocks, we use the fuzzer generated data, so the fuzzer data as a return values, for example, here, so that the application, so these mocks are dynamic and it simulates the application on all possible scenarios. And we will show how we automated this process. And the second two challenges regarding generating statefulness and generating good fuzz tests, we can automatically generate a fuzz test, a single test that tests all the public API at once. And this fuzz test just selects a function at random, a public API function at random, and it can select a sequence of function at random automatically. We'll see how this looks like in practice. But with this approach, you can very quickly have a setup where the open API or the public API is automatically fuzzed, and the hardware is mocked. So how this looks like on a high level. So we have the module that we would like to test, to fuzz, and in order to achieve good tests, results, or efficiency, we need to compile this on our Linux x86. And the main challenge, as mentioned, we have the public API that you would like. These are functions that are provided by the module to other modules to use, and this needs to be fuzzed. And we need to be able to mock the hardware dependencies to basically to replace or stop all calls to the actual hardware by fuzzer generated inputs. So each time an hardware dependent API is called, we just supply the fuzzer generated input, and we'll do the same also for the public API. And with this setup, we can think of it as, so all inputs to the application are fuzzed, and so the module is, on the one hand, it's compiled on Linux x86, providing very efficient setup, and all the simulated under all these circumstances that can happen, because at all external interfaces we provide fuzzer generated inputs. So how does it look like actually? So we start with the definition, so with the module definition that defines that configure the hardware dependencies and the public API. So which functions, and here we say which functions are external, so which functions are not implemented by this module. And then we have some special macros where we add annotations that describes the parameters there, and we use these parameters in order to generate the mocks. And we do the same for the fuzz tests, and we have some macros in this table that we can write for each parameter of the public API. And based on this configuration, that in our case it's a simple Excel sheet, we can generate both the mocks and fuzz tests that actually target the public API and feed the fuzz generated input there. Let's have a look at more detail, this in more detail. So now we need one table for documenting the mocking, so the function that needs to be mocked. So here assume that we have two functions, get x and get buffer. We say here, this is with these annotations, that the return value of this function is an integer of type int, because we have integers of different sizes. The same here, and we can dig into the code and see, okay, this char, this argument here is a buffer and it's 16 bytes, and then we can annotate here with write bytes and the number. And what we can generate out of this is the following code. So we generate a function, get x, with the same name, that returns an integer. And as we've seen, and this is the fuzz data provider, we return the value based on the fuzzer generated input. And we do the same, for example, for get buffer, where this buffer gets set in this application, where we get from the fuzz data provider 16 bytes, we copy them into the destination buffer, and we return also an integer base from the fuzzer generated inputs. The second ingredient that we need here is the API table, which we use to annotate which fuzzer data needs to land in each of the arguments. So here we say this is an argument of data, so it's a data buffer, and the second one is its corresponding size, and the bar API expects an integer, and then this flag is annotated with flag int arg int, so that the fuzzer can provide an integer value. And this is, of course, is then used to develop some simple scripts here that, based on this information, generates a fuzz test that actually call the code with these values. And as we'll see, it will just pick a function from a list at randomly and executes it. So we have statefulness and fuzz test automatic generation. And the result, of course, is that we have a fuzz test that can test the module in various situations, and it can call functions in different orders in order to simulate all the possible circumstances, and all the hardware dependencies are mocked and are replaced by fuzzer-generated inputs. And of course, so as a wise man once said, so talk is cheap, show me the code. So let's have a look at how this actually looks like in action. So here we have a, so of course I cannot show any of the customer code here. So we prepared a simple example where we have the some modules, the crypto module, GPS module, key management module, and time module. And so, for example, if you have a look at here at the GPS module, here it has some functions to get the current position, and we see here it has an external function. When this is a function that's not implemented by this module. And so what we need is we need to fill our Excel sheets that documents the mocks, the external dependencies, and the public API. And to facilitate this process, we created a simple Python script that actually parses the code and generates sort of a template that we can fill here. And let me go here, and I go to the Fuzzing directory. So here I would, let me remove those first. And the mock clip. So now we were here. So with the test generator, it's a simple Python script that we use to generate the code. So we just give it the include paths and the paths to the source and header files. Okay, and now the first step is to create a template, an Excel template that we can fill with the information that we just discussed. And yeah, for this we wrote a simple Python script that parses the source code and can generate this template for us for both the mocking, so for the mocks and for the API function. So what we can do is here we can say test so in order to facilitate the process of this configuration, so we didn't want to create this Excel sheet or this configuration file manually, so we wrote a simple Python scripts that actually parses the code and generate a template for us that we can fill in. In order to generate this template, I just call the script, need to provide the include paths and paths to the source files. So, and this is all what's needed. So now the source code will be parsed, and then Excel template here will be generated. And parsing the source code, we use a Python library called treesetter. You can also use clang also to do that. And so now we generated this template. Let's have a look at it. So here I can now open my this sheet, and I see I have some tabs here. So the stop step are the sort of the external functions. So these are functions that are declared in the module but are not defined here. And here I can, as we've seen, I can annotate the types here would be automatically detected, but we can just add our annotation. So this is here a return value that returns an integer, and actually it's the same for all of them. And yeah, here I can also say it's an an integer value. Now, so I just configured the return parameter of this function, and I see, okay, this function also takes parameters 2-byte arrays. So we can also write the macro so that these byte arrays are set by our mock. And for that, we just need to know how big these arrays are, so we can take this function name and see how it's actually used here in the code. So here is the corresponding C code, and we see here it's the first one is a byte array of 20 bytes, the second one is a byte array of 64 bytes. So we can see here, okay, for the first parameters, I want to write bytes of size 12. And here in the second, for the second parameter, I would like to write 64 bytes. So with that, the fuzzer, our script will generate a stub that actually returns an integer and sets these two data buffers based on fuzzer generated inputs. And we'll do the same for these functions that we also automatically detect. Then we need to fill these columns with a special annotations that we come up with. And of course, here in this, what we automatically detect is all functions that are actually declared and defined in the application, in the module. So if you want to discard some of these modules from, or these functions from the test, we can simply remove them from the table here. So just for time's sake, I prepared an Excel sheet here under API where these are documented. So we have a look at the stubs. We return an integer, and we do the same for these for the other parameters, and also annotated the functions. So for example, here, the key parameter is a struct of type crypto key. So I just say here, it's an argument of type struct, and the struct type is crypto keys. And what happens in the code is that this will be done in the code generation, replaced with a code that actually initialize this struct with fuzzer generated data. So assuming that now that we have actually filled this table with our annotations, we are ready to generate the fuzz test and the mocking library. So let's do it here. So now, if I go to the fuzzing folder where I would like to have the fuzz test and the mocking library, so all I need to do is to call our Python script with another option to generate the code, and I give it the path to our configuration file or Excel sheet where we documented the arguments and the return values of the API and the mocking lib and the extended dependencies. And now, if I execute that, we see that here 2 files have been generated, and let's have a look at them. So, and here we have the fuzzing, and so we have the fuzz test and the mocking library. And the mocking library is what we use to mock these functions. So we see here we're using fuzz data provider. So, and this is then initialized here by the fuzz test from the fuzzer generated data, and then we use this fuzz data provider to actually stop or mock the external function. So for example, this is the simple function that returns an integer. With our annotation, we said this return an integer of 1 byte, and then we simply use the fuzz data provider to provide integer of that size. And the same thing here. We have 2 buffers. So we have function that actually fills this this buffer based on the annotation that we did. So basically, this Excel sheet is sort of an API. It's a definition for the API for the external dependencies, and we use this definition to generate code that uses Fuzz data provider or use Fuzz data to initialize or to set the parameters and the return value. So here we set these two parameters in this function, and then we return an integer. If we have a look at our function, our Fuzz test, so we see here this Fuzz macro. So this needs to be replaced with LLVM Fuzzer this1 input. It is optimized to work with the product. So now we're just using a vanilla lib fuzzer target. So it's the normal LLVM Fuzzer this1 input. We see here we have the includes, and this is the interesting part here. We see what we in this target we have the Fuzz data provider. We initialize it with the fuzz generated data, and then we give it to the mocking library. So the mocking library is then able to use fuzzer data to provide for the mocks. And then we just say we'd like to pick a value from 1 to 100, and this value specifies which functions would I call in order. So which iterations, how long the sequence of function calls in a single iteration of the Fuzz target, and in each in each iteration we just select a function from the function that we define in our Excel table, and this function will then be called with Fuzz generated data. So for example here, the crypto calculate HMAC, we just create a string, we provide its data and size, and then we initialize the struct here with Fuzz generated data. And this is just with a single Fuzz target. Now, what we achieved is that with a single Fuzz target, you are able to call all public APIs in a randomized sequence that are selected by the fuzzer, and the fuzzer can then select which sequence are good in a sense that it leads to more code coverage or trigger new bugs. So now we're good to go. So all we have to do is just to compile the code. And so to compile the code, we just it's a CMake project that where we build our library, and then we use for the Fuzz test we add dependencies, which is the Fuzz test and the mocking library, and we just select here the flags that are needed by the Fuzz by CDANG in order to combine it for fuzzing and with the address sanitizer. And now if I can go to okay, let's create a directory to build the code. And now all I have to do is to simply run to build my code here. The code is built. I can just call make, and now we're done. And we created a Fuzz test, and that we can just, it's a normal lib fuzzer target. We can just start, and we see quite quickly that the fuzzer was able to find a bug, and that's here that we're attempting to double free. So double free bug. And we see also the exact location where it's happened. It's in crypto module 1.c. And if we go to the line 60 here, line 60, here, crypto module 1c, line 60 here. So we see we are freeing this pointer. So it's a current nonce is a pointer to a struct, and we're freeing it here, but we're not setting we're not setting it to null. So meaning that if this function is called 2 times in a row, it will try to free an already freed pointer, which is which is a bug that's reported by the address sanitizer here. So yeah, with that, and the fuzzer was able to find this by itself. So it was in this loop. So it managed to run this function. So one of the options that it selects, that it runs this function 2 times in a row. And so this gives an intuition how the fuzzer is able to sort of randomize or select the combination or sequence of functions that need to be called in order to trigger the bug. Yeah, so this is that's it actually for the practical example. And just to recap, so if you want to, what the approach is in a nutshell, if you want to use it for your own code, so we need a way to document the API, so the hardware dependencies and the public API. And we here in our example, we choose Excel as a format. We need to create a script. We need to create a script that parses this API documentation and create a mocking library based of it, where basically it replaces the arguments and replace the argument return value with fuzzy generated input. And we need a script that parses also this definition and generate a fuzz test that iterates over all the API functions and fit them with the fuzzy generated input based on the annotation you do. And just need to compile them and then stay tuned for bugs. For bugs. Okay, so thank you very much for your attention. I hope you get a good overview about fuzzing in general and the special challenges in fuzzing automotive software, and how you can actually come up with a very good and effective setup to fuzz automotive software. And with that, I conclude my talk, and I will be ready and happy to take any questions. Thank you.